All right, away we go. So I know what you're all saying to yourselves. What have you done with our professor, you sexy young man? Musical theater. I had to shave it for musical theater. So, huh? I've got a role in White Christmas at Chico Theater Company. And as soon as the run ends on December 22nd, it's growing right back. Alright, so the final push. I just realized just before walking in that I had failed to publish the screencast for Thursday. So I'll go ahead and publish that, and then today's stuff immediately following. In this final project, the main thing is animation blocks. And I do have some of these files you already have. I made some tweaks to them, so you might download and overwrite these. If you do it in Project 5, that's fine. It won't have any effect on existing code if you replace these in any of the projects. And then the tarball really doesn't contain much other than this README and tests. Also, I am not quite done with the write-up. So let me go through what I have so far. There definitely is more than enough there to keep you busy until Thursday, and I actually hope today to have it finished, but definitely before Thursday's class. Let's see, what's this doing wrong here? All right. Okay. So, yeah, oops, what is this? No, I forgot, there's another line I put here that says the tests that I've done so far. Alright, so there are a couple additional blocks that we need to implement. There are the initialization and the termination blocks, and if you go through the GPL manual, you can have, just as you can with the event blocks, you can have more than one of them. So you can have multiple termination blocks. You can also have multiple initialization blocks. And just as it implies, initialization would be, all those blocks would be executed before the main run of your program, and then the termination blocks would be run prior to your program ending. So in addition to implementing those, there are two more operators. I think these are the last two operators we need to implement, and that is near and touches. As you recall, those are for game objects, whether or not their proximity to each other. And then, of course, the animation blocks. Create the P6 directory, copy everything from P5 into P6. That's pretty good. Pretty easy, I should say. This is giving you a quick summary of initialization blocks and termination blocks. These things are super easy to implement. You'll have this done probably within 5 minutes or so of me stopping to talk. Stop talking, I should say. What you do with them is I need to look at code. Let's look at P5 code. Alright, so for these blocks, these event blocks that get executed on a keystroke, we get the event manager, and then we just add a handler, right? When you actually have done all the parsing of the block and you reach this particular production. the initialization blocks, all you do is this code right here, except rather you don't have a keystroke. Instead, there is hard-coded a couple keystrokes for you. And that, I say keystroke charitably. They're enumerations that are in that keystroke list of enumerations. So all you have to do is add handler with this keystroke or add handler with this keystroke, and that'll just add the blocks, and everything will work great. So real easy to get those going. There is a little bit of a kink with the terminate, which is, if you recall, there's a GPL exit function, and which will end your program right then. You do want to execute the terminate blocks prior to you leaving the program if GPL exit is called. So you need to go in there to the execute method of exit and have it execute all the termination blocks, and there it is, just one line of code. You get the event manager, tell it to execute handlers, and give it the keystroke. There's some tests to confirm you got all that going fine. Near and touches are also real easy to implement. You do have to add another constant class. So we have the double constant, the string constant, integer constant, game attribute constant, and now the actual constant for game objects themselves. The constants, let me look at, okay, the constants we have now, all these, of course, are fine. Keep in mind that this constant here is referring to a specific attribute of a game object, right? So it's a string or a double or an integer. This is the first time where we have to actually deal with an entire game object at the GPL level, and the only reason we have to deal with them at all is because that's how the near and touches operators work. You have game object near another game object, semicolon, or I guess that would return true or false, 1 or 0, and then the same with touches. And so we do need a constant for entire game objects just to facilitate our use of these two operators. So you'll add those, you'll add a asGameObject function. The way this always works is the base class contains all of these as functions, and the default behavior for these functions in the base class is to simply throw an exception, which is the actual type calling the function, and then all we need to do is override them in the classes that can use them. So asGameObject goes in the base class, and the only other place it goes is in the GameObjectConstant class, right? So if I look at what am I looking at? The integer constant. Is that right? As double. Right. What I want to look at is string. That's going to be the closest. So as string overrides it to return data. That's all it's going to be for the GameObjectConstant. You're just going to write asGameObject, and it's just going to return data. And of course, the data will be a pointer to a game object. Okay, so also very straightforward. You have to go ahead and follow through in the symbol, because obviously you need to be able to represent that as a symbol now that it's going to be used in expressions. And that's just going in and modifying this function and modifying this function in case you have an array of game objects or just a single game object. Let me look at my version of those functions. Okay, so this one checks on the type. I would add another case for, it actually provides some guidelines here. Don't make a case for game object. So the game object constant, you do specify that that object is of type game object. but for this you would use the specific types like rectangle, triangle, and I think I did something like rectangle, and then I just put all these cases like this, etc. for other 5, and then I just create a new game object constant underneath there. Really pretty straightforward. Then you have to go ahead and go into expressions where we actually wrote all of our operator classes, the plus, the multiplication, all those. And you have to create a class for near, a class for touches. All this goes back to project 3. We can look at expression.h for that. They're binary operators. So you'll have to write one of these for near, one of these for touches. The constructor is pretty easy. The evaluate function and type function is what you'll have to write in expression.cpp. And they end up being trivial to write because in order to implement near or touches, all you have to do is call the near or touches function, which is part of every game object. All right, so you're going to have something like what do I got here? The right-hand side, they're going to be specifically going to be game objects. There's going to be something right-hand side dot near left-hand side. It's going to be some version of that. That isn't quite what you need, but you get the idea. You're just calling a member function on the one game object, passing in the other, and it'll tell you whether they're near or whether they're touching. Once you get those in, you can use bin-off check with it. Comes together pretty quickly. 3 more tests to make sure the near and touches are all working. And then we get to the complex part of this project, which is getting animation blocks working. I've made the structure, let me back up. Animation blocks have 2 aspects to them. One is a forward declaration and then the actual block itself. Okay. I have redesigned this to be as close to C and C++ conventions of function prototypes and function definitions as possible. So this is very similar to a function prototype or a function declaration, which means that you don't need them in every circumstance. The only time we actually need a function declaration in C++ is if we are going to call that function or otherwise access that function prior to knowing what the definition of the function is. Right? And an obvious example is if that function definition is in a different file, but you could also potentially have it at the bottom of your C++ code, and so you have your function declaration, you call the function, and then the definition's down at the bottom. So that's a situation where it's required. This example code here is showing an example of it being required because I'm creating this triangle object and I am immediately setting its animation block parameter to dance. And so in this case, the parser needs to already know what dance is. So that's why we have that forward declaration. This here, I think everyone's aware of this, maybe not, but in function declarations in C and C++, these labels for the arguments are actually totally ignored by the compiler. Same thing here. It's simply not needed. The only thing that's needed in order to use, in this example, dance correctly is to know, 1, that it's an animation block, and that 2, its input parameter is a triangle. Right? Whatever you call this, it's ignored. That's that way in C and C++ too. Oops, I don't want to do that. Where would I have? Yeah, so for example, we have those there for readability, but That's all the compiler cares about in C++. So same idea. There are situations in GPL where you don't need this at all. And the question is, well, how can that be? Because you have to have all of your variables declared before any of your code blocks. So how could it be that I would have a situation where I don't need that? And an example would be is if I have GPL code that looks like let's see, I create a triangle and then I create animation, funky, and whatever you do, that's what I do. Okay, so here's an example of where I don't need that forward declaration because the definition of the animation block is appearing before I ever try to use it. So that's all the flexibility that is built in. And that's what basically everything that I was just talking about is what's being bulleted here. This was provided in an earlier project in order to get the earlier projects to compile, is a partially implemented animation code class. Let me pause for a moment and talk about why it's called animation code and not animation block. Your first instinct would be, well, why isn't the class called animation block? Because we have GPL triangles, and there's a triangle class, right? And there's GPL rectangles, and there's a rectangle class. We have GPL animation blocks. Why isn't there an animation block class? And the reason, and I made a little note of that in this write-up, is here, and it's a little hard to see. So here I'm creating a circle. That's not important. Here I'm creating two circles, hoop and wheel. I've got an animation block right here that takes a circle and it does something with it. Here, that is an animation block. This is this chunk of code. So that's the distinction, in that when you have an expression that looks like this, I would call that an animation block, and for the GPL type I would call that an animation block. This I would call animation code because it's referring to the code block itself. Okay? And then here's a different example. You can assign one animation block to another animation block. So that is why that's called animation code and not animation block, is so that we can distinguish this chunk of stuff from its use in expressions. Okay? That said, internally, this is represented as a pointer to the animation code class, and this is also a pointer to the animation code class. So under the hood in C++, everything's just pointing to this animation code class. But at the GPL level, there is a distinction between the two. Yeah?
So because the animation block is a data member, like a member variable in GPL would have like...
Yeah. So you have all these attributes, like this attribute is an integer of circle, this attribute is an animation block of circle. Yeah. Right. So what the animation code class consists of it looks like there's a lot there, but if I go to animationcode.cpp, that's it, 28 lines. There's really not a lot to this class, even though it looks like there's a lot to it. I would key in on the private data members. So in order for us to be able to use animation blocks in the GPL language, this C++ class needs to know the block name, in this case role. It needs to know the parameter name, in this case CIR for circle. It needs to know what the type of this is, which would be, we would store that as the GPL type, so that would be stored as circle in uppercase letters, that enumeration. And then finally, the block itself is exactly the same as all the event blocks we've been doing, which is basically a linked list of statements. So all you need is a statement pointer to the head of that list. Right? And so that is all the private data that we have for this class. What does the rest of this do? They're, by and large, a bunch of setters and getters for where they're required. They aren't. We don't need them for everything, but we need some variants. So we do need to be able to set the parameter name. Why do it? Again, the parameter name is in this case CIR for circle. Why do we need to be able to set that? Because if we have a forward declaration, we need to create an animation code object, but we don't yet know the name of the parameter, right? So when we get down to the formal definition, that's when we have this parameter, and we would need to set that at that time. Same, again, if you have a forward declaration, you don't have the code itself. So sometime in the future in parsing, we need to be able to provide our existing animation code variable with the block of code, the linked list of statements. We need to be able to get the block name. We need to be able to get the type of the parameter for things like error checking. Of course, there will come a time where the block gets executed and a game object is provided as an argument to the execute function. Finally, this doesn't show it here. There are 3 sets. These are static variables, so there's only one set for the entire application associated with animation code blocks. We need to, and they're all strings, and so they're just names of animation blocks. We need to know those we've declared with a forward declaration, those that we've actually defined, and then we need to know those that we're using. And by using, I mean here, dance is being used. Okay, so there's 3 different sets we keep track of. The reason is when we're done parsing, we basically need to do some set differences, some set subtraction to determine, have I done forward declarations but never defined the block? Right, that would be an error. That would be a linker error in C++. Do we have any forward declarations which are actually not ever used? That, of course, is perfectly fine in C++. I can create as many function declarations as I want. I'm under no obligation to actually use those. So we need to be able to note that. And then I think those are primarily the 2 reasons why we need to keep track of these. Again, my rambling for the past 5 minutes is just providing background. This then will go into detail on how you start to tie this all together and implement it. So all that talking is just background, understanding the purpose of this class. So now, how do we implement this? We have to enhance symbol because now a valid symbol in GPL would be to hold a pointer to a block of animation, an animation block basically. That just walks through adding it to symbol. That's pretty easy, not a big deal. There is an enhancement that we have to go back to table handler and symbol table, and we do have to add a little bit of code to them. It's not too difficult. Not difficult at all, actually. We need the ability to erase a symbol. And the reason is, whenever you hit a forward declaration, you are actually creating an animation code variable, and that is going into the symbol table. What we want to do before we run is we want to be able to identify all of those forward declarations where we never wrote any code for them and remove them from the symbol table. And you may ask, well, why is that important to remove them? The reason it's important to remove them is, if you recall, in standard out, it prints out the symbol table. It'll print out all those forward declarations if there is actually no code that's been defined. So it's just keeping things tidy and neat. So that's the reason why we implement those. They end up being real short and straightforward. And then we get to implementing the forward declaration itself. What do I want to go to? GPL. There are two production rules associated with forward declaration. I actually moved these together to make it easier to read. All right. So here's the forward declaration. You'll notice that all of these are terminal symbols. The word forward, the word animation, a variable, a name for the animation block, the left parenthesis, the right parenthesis. The only thing that is missing is, or I should say the only thing that isn't really a terminal token is this animation parameter. And what the animation parameter is, it's the object type. If you recall, object type is one of these GPL type enumerations. And then remember I said that this is ignored and is optional. That's the only reason there are two rules here. So that you can specify if you want for readability that it is ignored. This ends up being $$ equals $1. Same thing here. And then that GPL type for the object ends up being what is here. What would that be? 1, 2, 3, 4, $5 would be triangle or rectangle or whatever. Yeah.
And go back to the other one. So can you have an animation parameter with multiple object parameters?
No. So this is looking a lot like a function, and in many ways it is. And in fact, all the hassle we went through of creating a table handler that manages multiple symbol tables is to support this. Because it is so close to a function, we're actually going to find that we will push on an additional symbol table, create the symbol for this, quote, local variable, if you will, a reference, it's more of a reference, run the code, and then pop the table off. So even though it functions a lot like even though it behaves a lot like a function, it is not a free-form function. The grammar is only supporting a single input parameter. That single input parameter has to be an object type, meaning a triangle, rectangle, pix map, those 5. Yeah.
Why do we have such constraint? Why can't we have multiple objects as input to that animation block?
That's just the way GPL was designed. It'd be a nice, a little Christmas holiday to implement full-blown functions. So everything's in place. All you have to do is, if you want to adjust the grammar, you could relatively easily, you could enhance the grammar to support, call them generic functions with input parameters based on everything that we've architected so far. But just because that's the way GPL is, one parameter, it's a game object. Okay. So as I said, these rules down here are trivial. They're $$ equal $1s to bring that game object up here. This rule ends up being real short as well. All you have to do is create another entry for the symbol table. So this animation code class, you're going to create an object of that type, and you're going to shove it into the symbol table. Okay, so just a very small number of lines of code for this. Now we do a little bit of work to deal with the set difference stuff. I created a discrete item here and asked you to take a few minutes and write a test program and make sure you understand how set difference works and get it working correctly on a test program. We all know what a pain in the ass it is to debug this stuff. You don't want to be learning how to do set difference and debugging it in the middle of this huge application. Just write a little test program. I even provide the example of what you do. Create a set with these strings in it. Create a set with these strings in it. Subtract this first one from the second one. Let's see, if I get rid of 2, 4, 6, that should get rid of 2 and 4. That should leave 1 and 3 in the remaining set. So write a test program that does the set difference and then iterate through the result and confirm that you get 1 and 3 printed out. Okay? You do that, then you're all set for the next step, which is you need to be able to, as I said, take the declared block list, that is all of the forward declarations, and from that set of forward declarations you need to be able to subtract those that you defined blocks. This is a little gratuitous at this point because we haven't written any code for actually having animation blocks, so when you implement this, this will always be empty. But getting it in place now is going to keep things running smoothly. So what will happen is at this point in the game, all you can do is a bunch of forward declarations, and we can't yet define blocks. And if you look at the tests associated with that, create a variable just for the sake of creating it. There it is, 3 forward declarations. So here's the situation for, again, to repeat it, for why this is done, and I'll talk about where to do it in just a moment. Each time I hit these in this production in the grammar, it is going to create a teapot object in the symbol table. It's going to create a handle object in the symbol table and a spout object in the symbol table. Before I run the program, since I have not defined these animation blocks, I need to strip them out of the symbol table so that I don't get them printed out in that big mess of stuff that prints out when you run the program. So that's the reason when I take this list of these 3 things and I subtract what we know is an empty list, I end up with those 3 things. All 3 of those should be taken out of the symbol table then, so that they don't print out in the list of symbols. This should be the only symbol that prints out. Where do you do that? Where do you actually put this set difference? It is in the program production. Let's look at that real quick. There it is, the one that starts them all off. So you will not match this rule until you're done parsing your program, right? This is it. This is the end. Everything's been parsed. You hit this rule, you're done. This is kind of the start symbol to the whole grammar. So it's at this point, do set difference for each symbol that has been declared via forward declaration but not defined. erase from symbol table. That should get you through the first 10 tests. And then this is, then I actually only have 10 tests in there at the moment. This last bit here is we now need to be able to use animation blocks as constants and L values so that we can assign them to the animation block attribute of variables. And so we have to create another constant. This is for that animation code class. And it follows the same pattern as all the other constants that we have. You can see that it walks you through it, and then of course you just finish it after that. So the amount of work that I have here should be more than enough to keep you busy for 48 hours. What remains? Getting the locator version of animation code going. That again isn't going to be too difficult. Dealing with the assignment and being able to assign the animation code to an animation block. That's just enhancing the existing assignment class. And then that's about it. The only other thing would be the code associated with this production. And this is another one that I moved. Let's see. Oh, they're already close together. So an animation block, it consists of a declaration plus the block itself. The block itself, this actual token we have been using extensively. That ends up just being your linked list of statement pointers. This declaration is just all that preamble. The animation, ABC, triangle, try, right paren. That's what animation declaration is, and then of course statement block are all the statements that you created here. And then that brings it to completion. So I guess there probably aren't any questions. You got any questions? All right, then I need to give you 48 hours to try and crank through this. I definitely encourage you to try and get all this stuff done. It'll put you in really good shape to kind of breeze through the end of this semester in this class thing. Okay. All right, so 30 minutes. Let's see how many of you can finish in 30 minutes.